Hello everyone. I'm Catherine Sanchna, a PhD scholar from IIT Madras. This session, which is a tutorial session on mechanical characterization of bituminous materials, will happen every Tuesday between 6 p.m. and 8 p.m. Wherein we will be solving previous year's assignment questions, and also we will be discussing a few concepts which was discussed that particular week. So if you have this video will also be posted on YouTube, okay, the link for which will be provided by the NPTEL team in their website. And if you have any queries, you can either post it below the YouTube video, or you can ask in the discussion forum in the NPTEL website. Okay, so without any further delay, we will begin the class. So let me share my screen first. Okay, this week there were 5 lectures focusing on asphalt processing and usage, and also the chemical properties of asphalt. So what I'm planning to do this week is we'll go through the questions one by one, and um, and as an as when we arrive to each and every question, depending upon its content, we will talk about the talk in detail about the theory or theory related to it. Okay, so let us begin with the first question. Okay, so bitumen is what? Okay, so you know what a bitumen is. So long uh, we've been saying what viscoelastic materials are, that is the mechanical characterization part, okay, the modeling part, or how this material is tested. But just now we are coming to learn about what actually this material is about, right? Where are we getting this material from? So this is the heart and core of um, pavement engineering, right? Bitumen is the binding material, and it is important to know its source, its chemical properties along with its mechanical properties. Only then you will be able to relate why a bitumen is behaving in a particular manner, right? So Navita ma'am would have mentioned we are studying the chemical composition of bitumen because it is a naturally available material, unlike polymer materials where you specifically prepare the material for a particular to behave in a particular manner. In, you prepare it in such a manner that it has certain properties. Unlike that, bitumen is a naturally available material, and so its chemical properties has to be determined by us in order to relate why it is behaving in a particular manner. Okay, so why I started this is, so first we need to know how a bitumen is derived. Okay, so so if you ask where we get petrol or diesel from, everyone knows that it is obtained from crude oil, but no one knows where bitumen is obtained from. It should be known that this bitumen is also obtained from the same crude oil. So yeah, so you know that, sorry, yeah, just yeah. So you know that a crude oil is obtained from fossil fuels, like the preservation of fossil fuels, like the fossil fuels eventually turn into crude oil. So this crude oil has is very complex and has n number of fractions which we are using in our day-to-day purposes. Okay, so even if you see this column, okay, here this is our raw material, crude oil, and where is the material that we want? It is here. So after all this processing only we get this bitumen, and as I said earlier, bitumen is obtained from crude oil. But how is it obtained? So you know what a fractional distillation process is, right? So if you have a compound with many number of compounds inside it, then in order to separate out each fraction from that compound, you will subject it to something called as fractional distillation. Now you know what distillation is, right? Say if you have salty water, okay, water plus salt, okay. So if you want to separate out water from this portion, from this fraction, you will simply um, heat this container of water, and later when the water evaporates, okay, at its boiling point of 100 degrees Celsius, when it vaporizes, you will allow it to condense, okay. Maybe you will pass through a tube which has cold water circling around it, so that the vapor will condense to liquid, to water again. So the salt will be left behind in this container. So that we know that that is distillation. So if this is for so distillation is to obtain a single compound. If you know that your compound has only single compound, okay, you want only one single compound from that, then you will do distillation. A fractional distillation is, you know that the source has n number of compounds and each compound has different boiling points. In that case, what you will do is fractional distillation. What do I mean by fractional distillation? You will keep on heating the source, okay, or the crude oil in this case. Then at each temperature, with increase in temperature, you will get one particular compound, one particular compound, okay. So in this case, generally, in general, okay, this is not given in detail, there are actually a lot more compounds than this. So at a temperature, so this is at very low temperatures. So at very low temperatures, this portion will get separated out, okay. This will get evaporated, then you will extract only this portion. So this will happen at one particular temperature, say low temperatures, okay, low temperature compared to all the other temperatures, okay. Then say this is, say, 200 degrees Celsius. Then after a little more than this temperature, or closer to this temperature, from there you will start getting the next element, which is next compound, which will be kerosene. Similarly, you will get a lot of compounds, okay, and the final compound, okay, which is left behind after all the compounds have been extracted from this crude oil, the final compound is bitumen, okay. Why? Because this has the highest boiling point, okay, because it is extremely complex, and it is extremely complex, and it is the final portion that is left after the fractional distillation of crude oil. Now this crude oil, okay, further processing maybe we can see later, or I will explain it here itself, okay. So first, the crude oil will be subjected to something called as atmospheric distillation. So here it will have the presence of oxygen. Heating will happen in the presence of oxygen or air, okay. And then the final portion, which we call it as the long residue, okay, the long residue or the bitumen, okay, the bitumen or the long residue, will be again subjected to one more fractionation column called vacuum distillation, okay. And after this vacuum distillation, the final portion, again here also the final portion left behind, which we call it as the short residue, is our bitumen, okay. So first, the crude oil will be subjected to fractional distillation in an atmospheric distillation column. So this is one, and the final portion, the long residue, okay, will be again subjected to something called as a vacuum distillation, and so this is two. And the final portion, which is your bitumen or the short residue, it is not the bitumen that you actually directly put it in the field. We will see. So this bitumen which you get from here, the vacuum distillation, it can either be directly used in the field, or it has to be modified to achieve certain properties, okay. So that short residue, we will simply call it as bitumen here, okay. So as we saw, bitumen is the heaviest fraction of petroleum, okay. Next is, so this option is correct. Let us see if the next option is correct or not. Is there any difference between bitumen and asphalt? So in many places you would have seen people interchangeably using bitumen and asphalt, okay, right? But are they the same? The point is they are actually not the same. They have different chemical compositions, but they are not explained carefully, okay. So we interchangeably use bitumen and asphalt everywhere, but actually bitumen and asphalt are different, okay. So this is not the correct answer. Next is bituminous natural asphalt, okay. Nowadays we are obtaining bitumen from crude oil, okay. In earlier times people were able to observe bitumen floating on lakes, okay, and that bitumen they used it for many purposes including road purposes, okay. So a bitumen can either be obtained from a crude oil, or it was actually either obtained from crude oil artificially, okay, by processing it, or it can be obtained naturally, okay, over the lakes. Now what they refer here as bitumen is the um bitumen that is obtained by fractional distillation and not the natural asphalt, because nowadays we are not getting natural asphalt. So this is also not the answer. And is it an organic binder? No, it is not an organic binder, okay. Okay, so the next question is, a full depth asphalt pavement consists of what? So this question is out of the blue, but still I've added it here, okay, because you should be knowing the basic structure of the pavement layer, and what are the different other different pavement layers as well, pavement structures as well. So what an actual pavement layer will consist of, what you actually see on the road, right? So when you walk on the road, all you see is the black pavement, right? Black bituminous pavement. But do they actually simply take the black bituminous pavement and simply lay it on the road, lay it on the ground, and make it even for you to travel smoothly? No, they don't do it that way. They will prepare the surface before laying the bituminous material, because the entire system is supposed to take care of the entire system takes care of the load that is being applied on the pavement, okay. So you have to know what is lying beneath this black material on the pavement, okay. So first you will have the natural subgrade. It can be natural or it can be prepared, okay. So what do I mean by natural and what do I mean by prepared? So if your ground, the normal ground, natural ground, okay, if it has the required properties, if it has the required strength, okay, this strength is determined by something called as a CBR test. If it has the required properties, then you can simply lay the next layer just on top of this natural subgrade after compacting it, okay. Or you have to prepare the subgrade if it is not of the required strength. So how will you prepare the subgrade? You will take some other material in order to increase its strength, then you will compact it so that the final strength of the strength of the final mixture is the strength of the mix that you the strength of the final soil, okay, the compacted soil is the strength that is the final strength that you want. So this is your base, your natural subgrade or your prepared subgrade. On top of that you will have something called as the subbase, okay, and above that you will have something called as the base, and these two constitute of granular materials, okay. And on top of these two you have something called as a binder course, and above this you will have something called as surface course or wearing course. Okay, and these two are made up of bituminous materials, which is your bituminous mixture. Okay, now this is for a general, regular, conventional pavement. This is a conventional pavement structure. Now, what have they asked? They have asked a full depth asphalt pavement constitutes of what? Okay, by the name itself, you can say that the full depth of the pavement constitutes of asphalt. So, this base and sub base should not be there. That is, the base and sub base will be replaced entirely by the bituminous mixture. Will the subgrade exist? Obviously it will exist, because this bituminous mixture cannot be laid on air, right? It has to be laid on some substrate, which is the subgrade here. So on top of the subgrade you will lay the bituminous mixture, and this is called as a full depth asphalt pavement. So based on what I said, let us see which option holds true for this question. Okay, a full depth asphalt pavement consists of 3 layers of bituminous layer over a granular subbase, 2 layers of bituminous layers for a granular base and subbase, all the layers of bituminous materials resting on a prepared subgrade, a cement concrete subbase sandwiched between bituminous layers. So based on what I said, this option holds true, right? All the layers of bituminous materials resting on a prepared subgrade, right? Okay. So now moving on to the next question. If there are more carbon atoms in a compound, how will the boiling point be? So why have they asked this question? Okay, I told you that in fractional distillation, how we get the compounds? By boiling the crude oil, right? By heating or boiling the crude oil. So so you have this fractional distillation column, and when you have the crude oil, and by heating it, depending upon the boiling point of different constituents of this crude oil, each portion will get evaporated, okay, at its particular boiling point, and when you condense that material, you will get the required fraction. Okay, now you have to know when you have to cut, or let us say, let us take again water for example. Okay, water, and you have some other fluid, let us say oil for example. Okay, I don't know the boiling point of oil, but let us take for example, the boiling point of water is 100 degrees Celsius, and the boiling point of oil, obviously it has to be more than 100 degrees Celsius, let us say 150 degrees Celsius. Okay, I think so, it has to be more than water, I'm not sure, but still let us assume it this way. Okay, so let us say I have, and I am also not sure if this is a good mixture, but for example, okay, this is just an assumption. Only when I take very simple materials like this, it will be easy for you to understand. So let us say my water has 100 degrees Celsius, and the boiling point of water is 100 degrees Celsius, and oil is 150 degrees Celsius. Now I will keep on heating this mixture. Now I should know when I should condense, only then. So when it reaches 80 degrees Celsius, I will have no problem. When it reaches 90 degrees Celsius, I will have no problem. Okay, this I need not keep anything here for condensing the vapor, because no material would have evaporated by then. But when it reaches 100 degrees Celsius, okay, the water will start evaporating. Then I have to know the boiling point of water, only then I will be able to capture water. Okay, so I have to know when the water will start boiling, and when the next fraction will start boiling. Okay, so when it reaches 150 degrees Celsius, so this I have to collect separately. What I'm collecting at 100 degrees Celsius is water, so that has to be collected separately. Next, when it reaches 150 degrees Celsius, now my oil will start boiling, and that has to be collected separately. Okay, so that is why we talk about boiling temperature in this question. So how will you so the basic thing is, if a compound has higher molecular weight, then the ease of releasing the molecules into vapor, okay, is difficult, right? It is hard. So any compound with high number of carbon atoms will have higher boiling temperature, right? So that is the question here, but I just wanted to explain why this question of boiling temperature has come to this point, has come uh, in between here, okay? So you have to know the boiling point of a compound, only then you will be able to separate it from other compounds, okay? So the boiling temperature of water, the boiling temperature will be higher, okay, for carbon atoms, if there are more carbon atoms in a compound. Now if you see this, okay, if you see this, let me show from this figure. So when you do this fractional distillation, right, you can plot something called as a distillation curve, okay? So this is called as a distillation curve, where x-axis will have a cumulative percent volume, okay? So let us say this is my fractional distillation column, and say at a temperature of 100 degrees Celsius, below that itself, okay, my butanes and lighter fractions would have evaporated, okay? So let us say x amount of x volume of, or say 100, let us talk in terms of volume, x volume of 100 ml or 100 liters, for example, please, okay? So if 100 liters of butane and lighter fractions have been evaporated, okay, and then you have condensed it, and you have found you have obtained 100 liters of this fraction. Now from 100, so this is still 100 degrees Celsius, from 100 to 200 degrees Celsius, you are going to get something called as gasoline, okay? So this, let us say 150 liters, okay? So now how will you plot this curve? Okay, so this is percentage volume, okay? Like this, you have to find out the volume for all the fractions, and then you have to find out the percentage. Let us say this constitutes to 10 percentage. So here 10 percentage corresponding to this temperature will be this butanes and lighter fractions. Let us say this corresponds to 20 percentage, okay? Now in the x-axis you have to choose 10 plus 20, which is 30, because it is cumulative volume, okay? So this is how you will get the distillation graph. And as I said earlier, you have to know when you have to collect each fraction, okay? So if you take from 100 to 200 degrees Celsius, you will be able to get gasoline. From 200 to 300 degrees Celsius, you will be able to get naphtha, okay? So that is why the boiling point of a compound is necessary. The knowledge of boiling point of a compound is necessary, okay? So so this is the distillation curve for a crude oil, okay? So the next question is, the lighter crudes tend to have more water, okay? So for that, let us come to this figure. Okay, for that, let us come to this figure. Let us say I have something called as a heavy crude. Let us say I have something called as a heavy crude and a light crude, okay? How is this said? If I have two crude oils, say two crude sources A and B, how will I say one is heavy or one is light? How are they saying this, okay? It all depends on your distillation curve, okay? So what did I say? If a material has higher carbon content or higher molecular weight, it will have higher boiling point, okay? And if this So whatever portion, so if the material with higher boiling point, okay, it means it has higher molecular weight, right? And if this higher molecular weight compound is present more in that crude, you will call it as a heavy crude. So how am I saying crude to be a heavy crude? If it has a higher molecular weight compound, uh, the weight of the higher molecular weight compound is the proportion of the higher molecular weight compound in a crude is more, then I will call it as a heavy crude. If not, I will call it as a light crude. Okay. So let us take for example, they are saying that this curve is a heavy crude and this is a light crude. So how are they saying this? Let us say, so this is where kerosene is cut, okay, between 300 and 400, 300 and 450 degrees Celsius, degree Fahrenheit, okay. Okay, so all this is in Fahrenheit, okay. So let us say how much percent of, how much volume, percentage volume of kerosene can be is obtained from each crude, okay. So if you see for this curve, okay, for heavy crude, okay, this it is 16 percentage, and for the light crude it is 18 percentage, okay. So you know that here if you see this, gasoline, naphtha and kerosene are lower molecular weight compounds, and this light crude has 18% of kerosene, which is a lower molecular weight compound, than this heavy crude, which has only 16 percentage of kerosene, which is a lower molecular weight compound. So if this is 16 means, then this extra 2% will be found somewhere here in the higher fractions, okay, right. So any crude with if it has the the percentage volume of lighter fractions, then it is called as more percentage of lighter fractions, then it is called as lighter crude. If it has high percentage of more percentage of heavier fractions, then it is called as heavier crude, okay. So what are these lighter and heavier fractions? Lighter fractions are gasoline, naphtha and kerosene. So this lighter crude will have more of gasoline, naphtha and kerosene, okay. If you see this figure itself, you can see that gas oils and the residue are heavier molecular weight fractions because the boiling point is much higher, okay. So this is the answer to this question. Now moving on to the next question. Okay. So before we move to the chemical composition, okay, let us skim through all these questions and first finish questions related to asphalt usage and processing, okay. Just a second. So all this will come under, okay, here we have one question, okay. Crude with higher carbons have what, okay. Here if you see, they have used something called as cut point. What do I mean by cut point? I was explaining this all this while, but only thing that I missed is I did not use the term cut point. So here I will introduce the term cut point with what I said earlier, okay. Yeah, just a second. Okay, so here if you see, let me take this figure again from here. So the temperature at which, okay, I will get this naphtha fraction or this gasoline fraction is called as the cut point for naphtha or gasoline. I should know when to cut it off and take it, like when to cut, like when to at what temperature I should get, at what temperature will I get this particular fraction. That is called as a cut point. Okay. Now it is the same question then. Okay. So crude with higher carbon content, okay, will have a higher cut point when compared to low carbon crude. Correct? Because high carbon means higher molecular weight. High molecular weight means high molecular weight means higher boiling point, and here we cut at the boiling point, so higher cut point. Okay, so the answer to this is higher cut point when compared to lower carbon crude. Okay. So let us check for other questions. Okay. This we already saw. Select the characteristic features of lighter crude, right? So we saw what a lighter crude is and what a heavier crude is, right? Let us read these options one by one and see which one is correct. So here they have something called as API gravity. So we did not talk about API gravity, but let us see other points. Okay. So they've talked about carbon number. So what should a lighter carbon have? Lighter crude should have lighter fractions or fractions with lesser carbon number, right? Only then they will be evaporated they will have lesser boiling points. Okay. So lighter fractions are materials with compounds with lesser carbon numbers. So this you have to search for in this option. Now they are talking about cut point. Okay. So if the carbon number is less, then lesser boiling point, and if the boiling point is less, that is what they are calling as cut point. So lesser cut point. Okay. So you already have two options here based on what we saw. So it should have lower carbon content and lower cut point. So it is either this or this. Now, how should the API gravity be? So do you have any intuition of what API gravity is? Is it specific gravity? If it is specific gravity, then if it is a lighter compound, it should have lesser specific gravity. Correct? But API gravity is not specific gravity. Okay, it is related to specific gravity. Okay, by a formula. So let us see that first. Okay, so if you have to know what API gravity is, then it is given by 141.5 by specific gravity minus 131.5. Okay, now this API gravity, okay, this stands for American Petroleum Index. Now this API gravity is used to identify identify how heavy or light a crude is. Okay, so what we saw, a material with lower molecular weight or lighter fractions, if it has lighter fractions or lower molecular weight, then its specific gravity is expected to be lower, right? But its API gravity will be higher because API gravity and specific gravity are inversely related. Okay, they are inversely related. So for a lighter crude, specific gravity should be lesser, which means API gravity should be higher. Okay. Now, what will be the API gravity of bitumen? For that, you should know what the specific gravity of bitumen is, right? The specific gravity of bitumen will be anywhere between 1.97 to 1.020. Okay. So, if you substitute for this, you will get API gravity close to 11. Close to 11. Okay, which is the same as that of the API gravity of water. Okay, because the specific gravity of water is also 1. Okay, so a lighter crude will have higher API gravity, lower carbon number and lower cut point. So this is the answer to this question. Okay, so let us see other questions. So which crude has higher bitumen content? So here so there are again 2 new terms. Okay, before that we will first see with what terms we know. Okay, we know the term API gravity, and if API gravity is high, we saw that it is a lighter crude. If it is a lighter crude, it will have more of lighter fractions, and this lighter fraction does not constitute bitumen. Okay, so bitumen is a heavier fraction, so it should more amount of bitumen can be found in a heavy crude. Okay, so if the API gravity is high, so crude with higher API gravity will not have higher bitumen content. Now we know carbon content. We know what is called as carbon content. So any crude with lower carbon content, obviously it will not have higher bitumen content, because lower carbon content means lighter fractions, and so it will have any crude with lower carbon content will be classified as a lighter crude. Now they have something. Now we have 2 terms called sour crude and sweet crude. So as the name says, these crudes actually taste sour or sweet depending upon the amount of sulfur present in them. Okay, so this sour crude, okay, will have a sulfur content of more than 1.5%. okay, and this sweet crude will have a sulfur content of less than 0.5%. So how did they classify it as sour and sweet? Because in order to find out the sulfur content in bitumen in a crude, they actually tasted the crude. Okay, so and they found out that if the sulfur content is high, it tasted sour, and if the sulfur content is less, it tasted sweet. Okay, this is how they classified crude based on the sulfur content. Okay, so now a crude with it okay a crude with lesser sulfur content, or a sweet crude was found to have higher bitumen content. Okay, so the answer to this is sweet crude. Okay, so now let us move on to the next question. Okay, this also we will see now. Okay. Which of the following processes yield high temperature susceptible bitumen? Okay, so if you remember, I told you something about asphalt processing. One is So here you will pass the crude oil through a atmospheric distillation chamber. Then the residue, which is your bitumen, will be again subjected to something called as a vacuum distillation chamber, and this residue, so here you will get long residue, something called as long residue. Here what you get, you will call it as short residue, and this, okay, and this bitumen, okay, this is this, okay, what this long residue and short residue constitutes of is the higher molecular weight fraction, which is your bitumen. Okay, now this bitumen, either it can directly be used for paving or for other purposes like waterproofing or whatever, and or if it is not of the required grade. Okay, so if you see IS 73, you have a few specifications, right? Softening point, penetration, viscosity, right? So now if it doesn't satisfy that particular grade, okay, especially viscosity, then you will have to further process it to bring it to the required consistency. Okay, so for that they do it by two processes. Okay, one is called as air blowing and the other is called as component blending. So what will happen here is, in air blowing process, they will take the short residue, okay, subjected it to air plus heat, okay, for a long duration, because of which the chemical properties will change. And so when this chemical properties change, the physical properties like viscosity will also change. Now how will it change? It will increase. Why is it increasing? So if you know better about what we do in if you know better about something called as aging of bitumen, then you will know that if you subject the bitumen to heat or oxygen, okay, the bitumen will be aged, okay, because of which its viscosity will increase. So this is what you are doing here, right? You are subjecting it to air and heat. So this will chemically change the bitumen, change the chemical properties of bitumen, as a result of which the viscosity will change, and in this case it will increase because you are actually aging the bitumen. This is called as air blown bitumen. Okay, this you will call it as air blown bitumen. Now there's something called as component blending. So what is and this is called as blended bitumen. Okay, so what will actually happen here is, let us say you have two bitumen of higher viscosity, say let us say you have a bitumen of viscosity say 20,000 poise, okay, and something called as 10 poise, and you want something and you want a bitumen of viscosity 5 poise, okay, then you can blend these two bitumen, okay, in a particular proportion to get the bitumen of the viscosity that you want. Okay, so now how will you get this high viscosity bitumen? Okay, for that you will do something called as solvent deasphalting. So this is what you use for a component blending process when you require a bitumen with high viscosity, very high viscosity. Okay, so what is this solvent deasphalting? What you will do is, you will take the bitumen or the short residue and you will add a solvent to it. Okay. What the solvent will do is, it will solve the lighter fractions, okay, and you will have something called as the solvent plus lighter fractions together, okay. It will get eluted out, okay. You can separate it, and some portion will be precipitate or a residue will be left behind, and this will have a very high viscosity, okay. So this component can be used for component blending, okay. Now so this is called as solvent deasphalting. In all the three process, so in all the process that I said, okay. So after solvent deasphalting, you have to separate out the solvent, right? For that you will use the solvent extraction, okay. Only then you will get the final residue which has a very high viscosity. Now out of all these processes, okay, out of all these processes, this will give me a bitumen with higher temperature susceptibility, okay. Now you have a question on sweet crudes, okay. Sweet crudes typically have 0.5% of sulfur content, okay. We just now saw that, right? We saw that just now. So sweet crudes have 0.5% sulfur content, and sour crudes have more than 1.5% sulfur content, okay. Now next question we will see when we go to chemical composition of bitumen. First let us finish asphalt usage and processing, and sorry for not aligning it in the particular way, because I just thought of it now that we should first finish these questions and then move on to chemical composition of bitumen, okay. Now lower API gravity gravity of the crude oil corresponds to what? Low API gravity means it has a higher heavier fraction, right? So higher heavier fraction means the vacuum residue, the residue that is left behind after vacuum distillation, that is obviously the heaviest fraction, right? And that percentage has to be higher, okay. So here you have two options, okay, but one is a sweet crude, is a sour crude, and the other is a sweet crude, okay. So which option is correct? So here it is sour crude with higher percentage of vacuum residue, okay. So this will have lower API gravity, okay. So, and then all this comes under chemical composition. Yeah, so now we are going to move on to questions on chemical composition of bitumen. Just a second. Okay. So now let us see the chemical composition. Now you know that bitumen is this pitch black material, right? It is very difficult to find out this chemical composition or the structure of this bitumen. So they try to do this in steps, like step by step, different each one trying to characterize bitumen from a different perspective. Okay, one is elemental composition, one is molecular composition, and one is fractionation. Okay, so first, you know that everything is made up of atoms, right? So first they went from finding out what are the atoms present in, what are the elements, or what are the atoms present in bitumen. Okay, they try to find out what are the atoms present in bitumen, and they try to characterize um, based on this composition. So they try to find out the amount of carbon, hydrogen, nitrogen, sulfur. Okay, so what atoms are present in bitumen. So that is the elemental composition. The next level, what they did was, you know that the atoms combine together to form a molecule, right? So with this, so they went to the next level and tried to characterize using molecular composition, like um, how what could be the molecules present in bitumen. Okay, you know the elemental composition, right? You know that it has carbon, hydrogen. So based on that, you can have a guess, or you can determine, or you can you can try to find out what how these elements are arranged in a molecule, right? So based on that, they did this molecular composition. And now what they did is, these molecules, okay, um, they they don't know the structure of the molecules. Okay, the structure of the molecules is not known. So in that case, what they did is, sorry, here in molecular composition, what they did is, they just try to find out the molecular weight. They just try to find out or characterize bitumen based on its molecular weight, whether it has higher molecular weight, how much higher molecular weight fractions it has, how much lesser molecular weight fractions it has. That was done by this molecular composition. And the final one is fractionation. So what actually they did is, from this elemental composition, you can only know what elements are present. From this molecular composition, you can only know only what is the molecular weight composition in bitumen. But they don't know how these molecules are arranged, or the structure of these molecules. For that, they did something called as fractionation. And as and when we go further, we will try to find out, we will see what this fractionation is, and how they are characterizing bitumen based on this fractionation technique. Okay, so out of these three techniques, okay, so all three questions will more or less will fall under these three techniques. Okay, okay, and so we'll see each question clearly. Now, bitumen contains molecules that are dash in nature. Okay, so now if you see, so before this, no, let us go with each and every question itself, instead of explaining the entire explaining the entire concept in a sequential manner. Let us go with the questions, because sequentially ma'am has very clearly explained it. So let us go with the questions first, okay, so that we can see them more clearly. So bitumen contains molecules that are dash in nature. So let us see this: aliphatic, aromatic, cyclic, and all the above. Okay, now what does this come under? Okay, so here you saw that the word molecules is there. So here they are characterizing. So here um, so here it should be either this technique or this technique, but they don't talk about the molecular weight, but they talk about these structures. Before that, you should know what these structures are, right? So how the molecules are arranged is explained in fractionation. So we will see what these structures are. Bitumen will have aliphatic structures. Okay, what are aliphatic structures? They are straight carb. So one thing that you should notice is bitumen is a hydrocarbon, which means predominantly it will have only hydrogen and carbon molecules, and in addition to that you will have some heteroatoms like sulfur, oxygen, nitrogen, or you will have some just a second. Yeah. Okay, so it will have predominantly carbon and hydrogen, and heteroatoms like sulfur, oxygen, nitrogen, vanadium, magnesium, manganese, calcium, sodium. Okay, so all this, so the bitumen is so the elemental composition of bitumen is this. Okay, it has all these compounds, and when I do elemental analysis, I will be able to say what in what fractions are they present. Okay, so now in molecular level, I will be able to say the molecular weight distribution in that particular bitumen. Okay, whether it has higher amount of higher molecular weight fractions or lower amount of higher molecular weight fractions, all that can be understood in molecular composition. Now this fractionation, okay, so they try to understand the structure of these molecules, and they've come up with what they say is it will have straight chain compounds. Okay, so hydrocarbons, you know that, so mostly it is composed of hydrocarbons, right? So it can either be arranged in a straight chain called as straight chain compounds, or aliphatic compounds, or this straight chain can form a circle, and they can be called as and they are called as cyclic compounds or naphthenes. Okay, it is nothing but these straight chains are um, form a circle, okay, these straight chains form a circle, and that is called as naphthenes or cyclic compounds. Okay, or this cyclic compounds is these cyclic compounds, they can be either single bond or double bond. Okay, if it is a single bond, we called it as cyclics. Okay, and if it is a double bond, we will call it as aromatics. All this we would have studied in our higher secondary education, like 11th and 12th, right? Cyclics, aromatics, and aliphatics. Okay, the straight chain compounds also, they can be single bond, which we will call it as alkanes, right? Or they can be double bond called as alkenes, or they can be triple bond called as alkynes, and this you will call it as saturated bond, and these two you will call it as unsaturated bond. Now if these straight chain compounds form a circle, okay, mostly it will be double bonds. Okay, so that is, they are called as aromatics, and when these single chain compounds form a circle, they will be called as cyclics. What they say is all these compounds, we know that bitumen is a hydrocarbon now, and also it is very complex, so all these compounds are said to be present in bitumen. So that is what this question is about. It says that aliphatic aromatic and cyclic compounds are present in bitumen. Okay. Now the next question is, microstructure characterization is used in studies related to what? So when I told you, I said, when we started the session itself, we said that it is important to study the chemical nature of bitumen. Just a second. Right? It is important to study the chemical nature of bitumen. Why? I don't have any control over this material. Okay. So if I want to know how this material is behaving in a particular manner, then if I know the chemical composition, maybe I can say that this chemical behavior, this composition is high, and that is why this behavior, this mechanical behavior, okay, mechanical or rheological behavior is observed, or this chemical composition is less, and that is why this behavior is observed. So that can be explained when we that can be correlated when we try to study the chemical composition. Also we saw something called as aging, right? So whenever bitumen is exposed to heat or air, it gets oxidized, and so its chemical composition will change. Okay, so when the material undergoes aging, okay, its viscosity will generally increase, and when it increases, this is the rheological property that we observe by doing tests. Now if you see this aged bitumen, okay, so this is an unaged bitumen, okay, and this is an aged bitumen. So on aging, it has undergone age, it has converted to an aged bitumen. And if you try to see the chemical composition, you would have seen some new compounds that are formed, okay, on aging. So when you study the chemical nature, you will be able to understand the aging process also. And one more thing is, will you be able to understand the temperature dependent behavior of bitumen? Obviously you will be able to understand also the temperature dependent behavior of bitumen. Okay, so with decrease in temperature or increase in temperature, if you are able to observe some changes in the you will be able to observe changes in mechanical and rheological behavior, and you can always try to correlate with the chemical composition at that particular temperature. Okay, so here the answer is all of the above. So moving on to the next question, a higher weightage is given to larger molecules with higher molecular weight in dash. Okay, to understand this, let us first understand where this question is from. Okay, so now I told you something called as elemental composition, right? How will you experimentally determine this elemental composition? There is something called as CHNS test. And what will happen in the CHNS test? You will be able to find out the proportion of, or the amount of carbon, hydrogen, nitrogen and sulfur in this bitumen. Okay, and how will you do that? What you will do is, you will pass this bitumen, okay, in an oxidation column, or you will try to oxidize this bitumen. And then what will happen when you oxidize bitumen? These compounds, okay, these elements, carbon, hydrogen, nitrogen and sulfur, they will be converted to their respective oxides, which will be, say, carbon dioxide, H2O, NO2, SO2, okay, sulfur dioxide, nitrogen dioxide, okay, they will be converted to their respective oxides. Now they will be converted to their respective oxides, but they will be all mixed together. So these have to be separated. Only then you will be able to find out how much proportion is present. Now in order to do that, you will pass this through a gas chromatographic column. What will this column do? This will separate this mixture into different compounds. Like, it will separate out these uh, four fractions. Okay. Now when you, so each fraction, again you will pass through something called as a thermal detector, thermal conductivity detector. What this will do is, it will tell you what is the fraction and its quantity. I'm very sorry. So this will come under molecular composition determination. Okay. So what I'm saying is for elemental composition. Okay, I'm really sorry. I just messed up. Okay, so this is for elemental composition. So here for elemental composition, you have to understand you have to determine the elements present, the fraction of the elements present in bitumen, which will be, we will be considering only 4 elements, which is carbon, hydrogen, nitrogen and sulfur, and you will convert it into its respective oxides, and then you will be able to find out what is the proportion of these oxides and in what quantity are they present. Okay, so this is how you will determine the elemental composition. Now moving on to molecular composition, which is what is asked for in this question. Okay, so I said that in molecular composition you won't be able to you won't be able to say what is the structure of these molecules or what molecules are present, whether it is aliphatics or aromatics. You will not be able to say. Only thing which you will be able to say is how much amount of higher molecular weight fractions or lower molecular weight fractions does my bitumen have. Okay, so in order to do that, you will perform something called as a size exclusion chromatography. So what will you do in this? You will first mix bitumen with a solvent. Okay, and this mixture you will pass through a chromatographic column. And this column is nothing but a porous column, so it will have pores. Okay, porous. Now when you do this, okay, the larger molecules will simply pass through these gaps and come out, and the elute will come out faster. Okay, whereas the smaller fractions will go through each and every pore and will take time to come out. Okay, so based on what time it is coming, you will be able to know whether it is a larger molecular weight fraction or a smaller molecular weight fraction, and also you will be able to know its quantity. Okay, so now you know. So now you've collected the elute, right? Now from this you can determine 2 molecular weights. Now you don't know you just know that you've just collected the different molecular weights, but but you don't know the molecular weight of the entire compound, right? So in order to do that, they use 2 molecular weight formulae. Okay, one is a number average and the other is a weighted average. This is nothing but taking simply average of the molecules, molecular weights. Okay, so you will You will simply take, say you have molecular weights of m1, m2, m3. You will simply take average. This is your number average. Okay. What will you do in a weighted average? Okay, so your larger molecular weight, so here you will do a weighted average, which means you will give some weightage to each molecular weight and then you will try to find out the average. Okay, now why are we doing this? What we will do here is we will try to give higher weightage to higher molecular weight fractions. Okay, because higher molecular weight fractions and lower molecular weight fractions, they have uh, they constitute to different behavior of the material when talking about chemical composition. Okay, so that has to be considered. So in order to do that, we are doing a weighted average, and this weighted average, what we will do in a weighted average is, say I have a molecular weight m1 and m2. Let us say this has a molecular weight, so this and m3. Okay, let us take 3. Say one has a molecular weight of 5, the other has a molecular weight of 3, and the other has a molecular weight of 2. So the total molecular weight is 10, right? Now this is the molecule with the highest molecular weight. So this has to be given the higher weightage. So how will I give weightage to that? That is nothing but 5 divided by 10. So 0.5 is my weightage to this. The next highest molecular weight is 0.3, and this weightage will be 3, and this weightage will be 0.3, which is 3 by 10, and this will be 0.2. Okay, so now I have to find out average uh, by a weighted average technique, which means I will multiply each molecular weight by its weight. Okay, this is the weight that I am giving to each, let us say W1, W2 and W3. Okay, this is the weightage that I am giving to each molecular weight, plus 3 into 0.3 plus 2 into 0.2 divided by sum of these weights, which will always be 1. Okay, so you need not mention that. So this will give me the weighted average molecular weight. Okay, so what is it that they are asking is, a higher weightage is given to larger molecules with higher molecular weight in what? Weight average molecular weight. So what we saw first is number average molecular weight, and the second one is weight average molecular weight. Okay, now we saw what is done in elemental composition, what is done in molecular composition. In elemental composition, you will find out the elements, the composition of the elements, and molecular composition, you will find out the molecular weights. Now what will you do in fractionation? Okay, in fractionation, just a second. Okay, so here, yeah, so what you will do in fractionation? So in fractionation, you will try to fractionate the material in, like you will try to separate the material into different fractions. And how will you do that? So first I will take bitumen and I will add some solvent to it. So when I add some solvent to it, you will get two fractions. One is one fraction which is precipitated, and the other fraction which is the solute, okay, which the solvent has dissolved from bitumen. This precipitated is always called as asphaltenes. And this solute will can further be separated into different fractions. Okay, and these fractions are nothing but saturates, aromatics, and resins. Okay, and these are collectively called as maltenes. Now I told you that this bitumen is composed of uh, aliphatics, aromatics, and cyclics, right? So um, what what people have tried to do is they separated bitumen into different fractions. Now they are trying to assign what each fraction is composed of, what is the molecular structure of each fraction. Okay, this is just an assumption. So what people say is saturates constitute mostly of aliphatics, so they have lesser molecular weight. Next, aromatics will have aliphatics plus little sorry, it will have some aliphatics and cyclics, so it will have the high molecular weight higher than saturates. The resins will have uh, cyclics and aromatics. Okay, most of cyclics and less of aromatics. Then the molecular weight of resins will be more than that of saturates and aromatics, and this aliphatics will constitute more of this asphaltenes will constitute more of aromatics. Okay, so that's this will have the highest molecular weight. So this they have tried to assign these molecular structures to these fractions. Okay, now one thing that you have to understand is what solvent you will use here. Okay, based on the solvent used, the amount that is precipitated from bitumen, okay, will vary. Now if you are using a strong solvent, then the bitumen the solvent can dissolve most of the bitumen and only less amount of the precipitated portion can be obtained. Okay, when it is a strong solvent. When it is a weak solvent, what do I mean by a weak solvent? It has a lower molecular weight. Okay, or it is a straight chain compound. Okay, then um, then the so if it is a weak solvent, then the amount that can be dissolved by the bitumen is very less, and so more bitumen will be precipitated, more fraction will be precipitated. So if you see strong solvent, higher solute, higher solute plus lesser precipitate, higher solution. Okay, so we'll call it as solution. And weak solvent, the other way around. Okay, now our question is about this. If N-butanol is used as a solvent instead of N-heptane in the fractionation of bitumen, the following can be said about the asphaltene. Okay, so what is N-butanol? You know what a butanol is. Butanol has 3 carbon atoms, right? And so this is my butane. So this is my N-butane. Alright. Now for N-butanol, one hydrogen atom has to be replaced by an alcohol group. All means alcohol, right? So this will be okay. Now this is one compound or one solvent, okay, in this question, and the other solvent is N-heptane. So N-heptane has 7 carbon atoms, right? So heptane will have 7 carbon atoms, and if it is an N-heptane, it is these carbon atoms are arranged in a straight line. Okay. So compared to this, so when you try to fractionate bitumen using these two uh, solvents, which one do you think will yield higher as how much do you think will be the asphaltene content? What is your asphaltene content? How much will be precipitated? Okay, that is what they are asking. So we saw what an N-butanol and N-heptane is, right? Okay, I'm going to say that higher proportion will be precipitated. Why? Because you see what N-butanol is, it has only 3 carbon atoms, and N-heptane will have 7 carbon atoms. So it is a stronger solution, and when it is a stronger solvent. So when it is a stronger solvent, oh, just a second. Okay, this must be because of the alcohol group. Okay, so maybe N-butanol is the stronger solvent. Okay, I just judged based on the number of carbon atoms or the molecular weight. It can be because of the alcohol group also. So the strongest solvent can be N-butanol, and because N-butanol is stronger solvent, it can precipitate out. It can dissolve a large amounts of bitumen. Okay, and lesser amount of precipitate will be remaining. Okay, so here the option is asphaltene content will be higher, or higher amount is precipitated. Wait, just a second. I just confused you people. Let me take this question, and from next time let me stop scribbling in this slide, and I will scribble in this slide. Okay, so yeah, asphaltene content will be higher, so higher precipitation. If it is higher precipitation, then the solvent is weak, so weaker solvent. Okay, and we saw why it is a weaker solvent. So what we said earlier is correct. Okay, so because N-butanol has only 3 carbon atoms and N-heptane has 7 carbon atoms. So this is a weaker solvent, so it will dissolve only lesser portion of bitumen, and a large amount of bitumen will be, a large fraction of bitumen will be precipitated, and this precipitated portion is nothing but the asphaltene fraction. Okay. Okay. Now moving on to the next question. So identification of specific functionalities in bitumen can be performed using the following technique. So here you have to understand that CHNS analyzer is used for elemental composition determination, right? So it is for elements. If it is functionalities, say a CH2 functionality or CH3, okay, these are all functionalities. So in order to find out the functionalities present, we will use a FTIR spectroscopy technique, okay. So right, yeah. Now moving on to the next question. This we already saw. Okay. This also we saw. Bitumen is the heaviest. Yeah. Okay. Which among the following fractions have the highest molecular weight on an average? When I explained this fractionation technique itself, I told you that I have something called as asphaltenes, okay, then resins, aromatics, saturates, okay. And this asphaltenes, we saw it will have more of aromatic compounds, okay. This will have more of aromatic compounds, okay, and this will have some aromatic compounds and cyclic compounds, okay, and these two will have heteroatoms also, okay. So what do I mean by heteroatoms? Apart from carbon and hydrogen, we saw that it has sulfur, nitrogen, vanadium, manganese, magnesium, oxygen, sorry, magnesium, manganese, oxygen, calcium, yeah, sodium, right? So these contribute a lot to the behavior of bitumen. Why do I say this? Because these have higher polarity. When your molecule is when any component, when any molecule has higher polarity, then it tends to react more, okay. If it tends to react more, even if it is present in small fractions, it is going to react more and create a huge difference in the chemical composition, right? So these are higher components with higher polarity, and these will be present more in asphaltenes and resins, okay. So this you have to I will tell you why I told you this, okay. Now, so aromatics will have cyclic compounds and straight chain compounds, okay, and this will have more of straight chain compounds, okay, and branched chain compounds, okay. Now if you see from this figure itself, the molecular weight keeps decreasing, okay. We will call this as SARA fractions: saturates, aromatics, resins and asphaltenes. The molecular weight keeps decreasing, okay, in this order, and the polarity will keep increasing in this order, because these two will have higher number of heteroatoms, okay. So this is the trend for molecular weight and polarity. Now they've asked you which among the following fractions of bitumen have the highest molecular weight on an average. So if you see, the asphaltenes have the highest molecular weight. Here you see two new terms, which is naphthene aromatics and polar aromatics. This is nothing but this is aromatics. You saw what naphthene is, right? Naphthene are cyclic compounds, right? So naphthene aromatics, this has mostly cyclic compounds. So naphthene aromatics is nothing but aromatics, and this is polar aromatics. So this is resins. Why these are resins? Because polar aromatics are these aromatic compounds with double bonds, and they have higher polarity, right? So these are resins. So just the names have been changed, okay. So asphaltenes have the highest molecular weight on an average, okay. Now moving on to the next question. Dash is the most abundant element present in bitumen. This we all know. Bitumen is so these are present in small amounts, okay, heteroatoms. And bitumen is a hydrocarbon, and it has large number of carbon atoms. So the answer to this is carbon. Okay. Now, moving on to the next question. We already saw this earlier. Heteroatoms are highly what? They are highly polar in nature. Okay. Okay. Now the next question. As the carbon number increases, what will happen? Okay. For this, if you see, there's something called as isomers. What are isomers? If you see, two molecules, let me take one example. Okay. This is the molecular formula. Okay. How can I arrange these two? Let us say that I'm simply giving you the molecular formula, and I'm telling you, give me a structure with this molecular formula. Okay, structure of the molecular compound with this molecular formula. Now you can arrange it in different ways, right? You can say that I will arrange it like this. Okay, 4 carbon atoms. I've arranged it in a straight line. Okay, with hydrogen atoms attached to it. Okay, this will give me what this is in butane. Okay. Or I can do one thing. Why should I arrange 4 carbon atoms in a row and hydrogen atoms to it? I can arrange 3 carbon atoms in a row, attach hydrogen atoms to all these places here, and to one place I will attach a methyl group. Okay. Now count the number of hydrogen atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here also you have 10 hydrogen. Here also you have 10 hydrogen. Here also you have 4 carbon. Here also you have 4 carbon. Now this you will call it as, this is a structure for pentane, right? So pentane, this is pentane, but there's a methyl group attached to it at the second carbon atom. So you will call, this is 2-methyl pentane. Okay. Now this is the IUPAC name. Okay. Colloquially it can be called as isobutane. Why it is called as isobutane? Because it is very similar, it has the same molecular structure as that of a butane, N-butane, but it is an isomer. Okay, it has a different structure. So these two compounds, okay, molecular compounds have the same molecular structure, have the same molecular formula, but different structures. So how do you think their behavior will be, the physical behavior? Even the boiling point of this N-butane will be very much different than this isobutane. So even a slight change in the molecular structure, even though they have the same molecular formula, they will have different physical properties. Now this is for a bitumen, this is for a material with, this is for a molecule with 4 carbon atoms. Now you can, instead of attaching this methyl group here, you can attach this methyl group here also. Then you will call it as 1-methyl pentane. So that will have different physical properties, and that is also an isomer. Similarly, For a material with four carbon atoms itself, you are able to see that there are at least three structures. Okay, three or two structures. Yeah, three structures, right? One, two, and one more with methyl group here. Now, what about our bitumen then? A bitumen, so more the number of carbon atoms, more the structure or more number of isomers you will be able to get, right? Now our bitumen has n number of carbon atoms, okay, and so it will have n number of isomers. So this I wanted to add here, though this is not the question. Okay, so now if you see the question, as the carbon number increases, this question we already saw earlier. Molecule with higher carbon number will have higher molecular weight. Why it will have higher molecular weight? Let us see one more example. Okay, first let us finish this question and go. So a molecule with higher carbon atom will have higher molecular weight, okay, and the number of isomers will also be more, okay. Molecular weight and the number of isomers increase, okay. So one more thing that I wanted to say from this is, since we are talking about molecular weight here, when we did this elemental composition, we will be able to quantify something called as H by C ratio. From this we will be able to say only we will be able to say if the molecular weight of the bitumen is high or low, okay, but you will not be able to characterize you will not be able to find out the molecular distribution in bitumen. That is why we moved from elemental to molecular uh, composition for characterizing bitumen, okay. So when I say H by C ratio, how did they say whether the material had whether the compound bitumen had higher molecular weight or lower molecular weight? So how they did is, if the H by C ratio is less, then the molecular weight is less, okay, and if it is more, the molecular weight is more. Why? Let us say my H by C ratio is 1, okay, and here let us say my H by C ratio is 3. So for one hydrogen atom there is only one carbon atom in this case, and here for one hydrogen atom there are 3 carbon atoms. And what is the molecular mass, molar mass of carbon? It is 12.0 something, okay. And let us say roughly we'll take as 12, and hydrogen, the molar mass is 1, right? So obviously this molecule or this bitumen with a H by C ratio of 3 will have a higher molecular weight than, so even if it has one hydrogen atom in the bitumen, it will have 3 carbon atoms attached to it, right? So obviously the molecular weight will be higher. So that is what you can infer from an elemental analysis when you want to say something related to the molecular weight from this elemental analysis, okay. But a molecular composition, okay, if you do this molecular composition, you will be able to say the molecular distribution, okay, see the molecular distribution. Okay, moving on to the next question. Which among the following element cannot be quantified through elemental analysis? So elemental analysis, we saw a test, right? CHNS test. From this itself you can see, from this elemental analysis you will be able to quantify how much carbon, hydrogen, nitrogen and sulfur is there, but not oxygen. So the answer to this is obviously oxygen, okay. Now the linear long chain compounds present in bitumen are termed as what? Okay, so here is it called as aliphatics? Yes, because they are the linear long chain compounds with or without with single, double or triple bond. They can be anything, okay, but they are linear long chain compounds. Aromatics, we saw they are cyclic structures with double bond, and cyclics we saw they are simply these long chain compounds connected in a cycle, okay. It can be this form or this form, okay, like this, okay, and these are called as cyclics. And ring compounds, okay, both these two are same, okay. So the answer to this is aliphatics, okay. So moving on to the next question, a higher percentage of the heteroatoms are observed in the dash fraction of bitumen. Okay. So we saw heteroatoms. When I explained the Sara fractions itself, I told you they are present more in resins and asphaltenes, and even more because the polarity keeps increasing. Yeah, we saw that, right? So we saw that, right? So asphaltenes will have the highest percentage of heteroatoms. Okay. Now moving on to the next question. Yeah, one second. A higher weightage is given to this, we already saw, right? Weight average molecular weight. Now okay, so moving on to the next question. Molecules having same chemical composition but different structural arrangement are called as what? Just now we saw what isomers are, and I also gave an example. Now arrange the following fractions in the correct order of their polarity. So I said Sara fractions. This is the increasing order of molecular weight and increasing order of polarity. Just a second. Okay. So this is decreasing molecular weight. Okay, so let's not confuse, because I remember drawing the arrows in opposite direction. So this is decreasing molecular weight and increasing polarity. Okay, this is what I meant here when I explained. So increasing molecular weight and increasing polarity. So the answer to this is asphaltenes. Okay, asphaltenes will have the highest polarity, followed by polar aromatics, followed by naphthene aromatics, and then followed by saturates. Now this is the last slide. So this we already saw in butanol, right? We saw the fraction of bitumen that is insoluble in a solvent. This also we saw, right? It is more or less related to this question, where when you uh, do this fractionation technique, you obviously subject bitumen to a solvent. You add a solvent to bitumen, right? And you will get two portions, which I said. One is asphaltenes, which are precipitated, and the other is maltenes, which are dissolved and which are the saturates, aromatics, and resins fractions. The answer to this is asphaltenes. So this is what that is it for today. So we will meet next week, okay, with next week's contents. Thank you.